Hi everyone, my name is Courtney Krystek and I'm going to be presenting today on dark matter and dark energy and its nature in the universe. Now, using Einstein's theory of gravity, when we started embarking on our space explorations, there were certain things that we expected to find in the universe. For one, we didn't expect the universe to still be expanding at the rate that it is today. Now, a lot of theories surfaced once we discovered this, and one of them was that of dark matter and dark energy. Now, the dark matter and dark energy theory states that there is a form of matter whose properties we don't quite know yet that is acting on the universe, in all the stars, and it's affecting their movements in certain ways. In fact, there's even an idea that about 80% of the universal material is made of this, and only 20% is the visible material, as you can see on this graphic here. Now, the interesting thing about dark matter is that we haven't been able to pinpoint exactly what it is, but we have been able to pinpoint exactly what it isn't. So the good and the bad there. We've done many experiments and run many hypotheses into probing what dark matter could be, such as antiparticle analysis, and different experiments like that. Since it's not visible to us, we're not able to use the regular methods of understanding we might otherwise use in astrophysics, such as looking at the temperature, the color, these kind of properties. So the way that astrophysicists today and in the modern research field have been probing dark matter to try to understand more of its properties and more of how it affects our universe is by looking at how it interacts with the visible objects that we can measure, that we can see. And by doing it in this way, we're still able to get the statistical data that we need in order to see, yes, this is having an effect and this is what it is doing, this unseen force. So it enables us to back up that hypothesis that, dark matter does exist, and it allows us to guess more at its properties. One especially interesting study that I'm going to be discussing in this presentation is looking at binary pulsars and how dark matter interacts with their movement. There's evidence that has surfaced through observing two binary pulsar sets that I'm going to go over, and the effect of dark matter seems to be modifying their movements. There's a scenario called the double disk dark matter scenario, and it looks at the curve of their movements around each other, and they're not moving how we would expect. And by analyzing this, we can suspect that part of it is due to the dark matter and the dark energy that we can't see. And by looking at the visible effect of it, we are able to better understand how it's operating in our universe, because dark matter and dark energy not only affect these distant stars and encompass our imaginations as to what the cosmos is built of, but it's the very fabric. It could be the very fabric of the universe. It could be a property that we have yet to really delve into, just as gravity is here on Earth. So that's why it's so important and interesting to understand and to make sense of. So how did we first come up with the idea for dark matter and dark energy? Let's begin there. Now, there was an astrophysicist by the name of Vera Rubin who was studying spiral galaxies, and she hypothesized that we would see the extending arms of the spiral galaxies as you move out from the center to be rotating more slowly. But upon further analysis, she realized that they were actually speeding up, in that at the best case scenario, they were coming to more of a plateau, but they were not slowing down as we would expect matter to behave. So this is where the first proposition for dark matter came upon us. And it's also important to note here that dark matter and dark energy are general terms because we don't know enough about their properties yet to definitively say this is what it is and this is what it isn't. And That's one thing that makes it so fascinating. Now, I've already gone into some of the experiments that have been conducted in recent years to determine what dark matter is not. And through all of that, the most likely conclusion a lot of researchers have drawn is that dark matter may be made from like super particles, and ones that we haven't actually been able to see yet. One of these supersymmetric particles is called an axion, and the issue with this is that, again, we can't see it. We can't see its movement. So they're actually conducting at the research center of CERN, trying to recreate what dark matter may be. And one of the issues is that they wouldn't be able to see if they did create one of these particles because it would just pass through. But one way of detecting it is by having it pass through and then seeing how it affects the visible matter in the area, seeing if it leaves a trace, so to speak. And this would give us more of an idea of what it is. Another hypothesis on dark matter, that again, we need some more data. Right now it's just mathematically, it's been worked out in mathematical philosophy and mathematical models, and it pertains to the multiverse. This idea is that rather than being a substance like matter, just a matter that we can't see that works and appears differently than what we know, the effects that we're seeing of dark matter on the universe might just be pockets of different universes, and this corroborates with the idea that there's a multiverse and we are just one pocket of a universe among many, and that the reason that we see these different kind of pouches in the universe in different spots and effects is that instead of it being like a matter interacting on visible matter, it might just be another universe that we can't see acting in on our own universe. And this would affect the gravity, it would affect all of these different properties of normal matter. So that's another intriguing model to think about. And it takes me back to realizing that there is much that we don't know about this topic, and there's much to be discovered and explored still. And I think that's very exciting. And it's also humbling to note that what we know about the universe is just a tiny, tiny fraction of what is out there. That our eyes are still so closed to these properties, and that we only know this 1% about how the universe operates, what it's made of, how it began, why is it still expanding, all of these questions. So now I'm going to move on to dark energy and discussing that. And dark energy is said to make up around 68% of the universe. Dark energy appears to interact with the vacuum in space, and the idea of dark energy is that it's almost like, picture a curtain that is stretched all the way through the universe, and the dark energy is within that curtain as maybe like these little dots. And as you stretch the curtain further, as the universe expands further, these little particles and dots, they're getting evenly distributed throughout. So that's the intriguing thing about this so-called dark energy, is that even with universal expansion and the dynamic changes that the universe and other star systems and galaxies experience, that dark energy is still evenly dispersed among them, that it's this property that is within the universe. This means that dark energy does not have any gravitational effects, but rather just affects the universe as a whole, which is pretty cool. And it gives a lot of the different forces and the different properties that we are seeing, such as like a repulsive force that we see. And it also is a reason that we've come to terms with for why the universe is still expanding and why it's accelerating in its expansion, is that this dark energy, this curtain, so to speak, is helping that along. And we have used different observations to try to corroborate this idea, such as the Hubble law. And these measurements have allowed us to see just how much of this may exist. Now I'm going to talk about some of the more recent research that has come out about dark matter. And one research article in particular that caught my interest was about binary pulsars and how they can be used to determine the effects of dark matter on neighboring objects to try to determine its composition and how it affects the universe. Now, this is these observations are conducted by looking at the binary pulsars' movements and determining how they are affected by dark matter particles that we can't see. The hypothesis for this rests upon something called the double disk dark matter scenario, which is the idea that a portion of the dark matter actually settles into like a thin dark matter disk. And they measure the effects on the binary pulsars through this dark matter disk, so they can see how it's interacting with the movement. One thing to keep in mind about the double dark disk matter scenario is that it is, again, another just hypothesis model, and we do need more observational data to really support it. There are two approaches that this study took to determining how this proposed double dark matter disk was affecting the orbital period and rotation of the binary pulsars. One of the approaches was called a collisionless approach, and the second one they used was called a fluid approach. Now, these two approaches just kind of identified the way dark matter may interact with the visible matter. And this is important because it gives us a way to further study future binary pulsars and see how dark matter may be affecting them. We can use this study that was published as sort of a standard resource and move forward from there. And that's how the authors also concluded it, is that this provides sort of a model for furthering our knowledge into dark matter and how it affects different visible matter in the universe. So dark matter and dark energy are these two concepts that are still a little ambiguous to us. We know that the universe is still expanding. We know that its rate of expansion is increasing, and we know that there are properties that we have not yet defined that are affecting visible matter and properties of the universe itself. Now, dark matter and dark energy, they give us an avenue for discovering and explaining these coincidences and why these different patterns we can see are happening in the universe. And I think as further mathematical models progress and we are further able to observe what's going on and the effect of dark matter on neighboring visible matter, such as the recent research study into the binary pulsars, if we can repeat these studies and we can further them, maybe we can find out more about the properties of this mysterious matter and energy. It's incredible to think that our ancestors, thousands of years ago, they were looking up at the stars and they didn't know what they were. They didn't understand all the things that we understand today. But even with the tools we've been given of how much we can tell about a star and about a galaxy from the light it emits, from its luminosity, from the color, all of these things, lens blurring effects, it's crazy that these things, they don't explain dark matter and dark energy as much because it's that thing that we can't see. And that's really what's incredibly fascinating about it. I will certainly be keeping an eye out for future research into dark matter, dark energy, and also different mathematical models such as the multiverse to see how far we go in our explorations of that and what we come to find out. I think there are many properties yet to be understood about our universe. And I think part of our human exploration into that is important, and it's a journey that we are taking as a species. All right, well, thank you for listening to my presentation on dark matter and dark energy.